limits, we can find them either graphically, analytically, or numerically. I have a video on the intuitive idea of limits, which is really looking at how you find limits graphically in several different situations in a graph. That video is noted in the description of this one, and I've put a link to it. What we're going to do in this video is look at what if we want to try to get the start foundation for finding limits analytically. Now, to do this, we need to not only get some basic limit ideas, but we also have to get some properties about limits so we know how to work with them if they are acting on products or powers or quotients or additions or subtractions of different functions. We'll start with just some basic limits and some examples, and then we'll go on to some rules of limits after that. Now, this won't be the whole set of things that would be possibly asked of you about limits, but it'll give you a start. And as we go through, I'll post more limit videos that will help you get even a stronger foundation. So let's see where we have at some just a few very basic limits. These three help me get a start. So the first one here says the limit as x approaches c of b is equal to b. Now remember, when you're talking about limits, you need the components where you've got the LIM abbreviation for the word limit. Under that, you have to say what your variable of your limit is approaching. So here, as x approaches c. And then after the limit, you have to have the expression that the limit is acting on. So you need all of those three parts when you write out the idea of a limit. Remember to do that. Make sure that you don't just put in a few things and not all of it, or it's not giving the full idea of where you're looking and what the function that you're looking at is as well. So now let's think about this graphically. Remember, when we have just a number here, and I know it's a number with respect to this limiting process because it doesn't match the letter of the variable of the limiting process. So really, this is the limit as x approaches a value of a number. So when I look at that, if I have something like the limit as x approaches, say, 2 of a number, so I'm just going to put maybe 4 here, and I want to know what that is. Well, graphically, this is y equals 4 for the graph that I'm looking at, and y equals 4, remember, is just a horizontal line where y is always 4. So if I have my x and y axis, I have 1, 2, 3, 4, a horizontal line at y equals 4 is the graph. And on this graph, I'm saying what are the y outputs, so the limit is what are the y outputs approaching as your x gets closer and closer to 2 from both sides. So as my x is getting closer and closer to 2, as I'm going closer and closer to 2, my y's, well, are 4. For this particular example, y is always 4. So my outputs will be approaching 4 as my inputs are approaching 2. Now, how does that match up with what this rule says? Well, the limit as x approaches a value of a number is that number, because the output is always that number. So there's an example of that first one. Now, the next one is the limit as x approaches c of x. So notice here, this part of the notation that it's acting on matches the letter of the limiting process. Now, when I graph my function y equal x, well, y equal x is a line through the origin with a slope of 1. And so if I were to do a problem associated with this one, something like the limit as x approaches 3 of x, well, if I look at my values that are on y equal x, 0, 0 is on y equal x. 1, 1 is on y equal x. 2, 2 is on y equal x. Negative 1 is on y equal x. Y equal x is all the ordered pairs where the x coordinate and the y coordinate are the same. So as I look for what the outputs are approaching on this line, when my x's are approaching 3 from both sides, well, as my x's are approaching 3 from both sides, my y's are approaching 3. So the limit as x approaches a number of x is equal to whatever that number was that the value was, the variable of your limiting process was approaching. And then the third one for just this introductory part of it is the limit as x approaches c of x to the n, where n is a positive integer. So positive means it's got to be greater than 0. Integer, it has to be the greater than zeros out of the 0, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, etc. So the numbers that are positive out of that set would be 1, 2, 3, 4, 5, 6, 7, etc. So my exponents on my variables so far, we'll learn about other ones as we go, but here they're going to be a positive integer. An example of this would be something like the limit as, say, x approaches negative 1 of x squared. And here, my limit as x approaches negative 1, so c is my negative 1, of x to the 2 is a positive integer. And I just picked that as the example that we were going to go through. Now, if I think of this one graphically, I want to think, well, my function is y equal x squared. So if I graph that, that is a parabola with a vertex at the origin. So when x is 0, y comes out 0. When x equals 1, y comes out 1. When x equals 2, y comes out 4. When x equals negative 1, y comes out 1. When x equals negative 2, y comes out 4. And so we get our graph of our parabola. And we want to know what the outputs of this function are approaching as x approaches negative 1 from both sides. So here's my x value of negative 1. And as I follow the curve and look at what the y outputs are approaching as x approaches negative 1, they are approaching a y output of positive 1. Now, where did the positive 1 come from? It came from negative 1 quantity squared. So that's why this is saying that the limit as x approaches c of x to the n is equal to c to the n. Now that we have those, and we've kind of looked at graphically why it makes sense that those are the rules, here's the thing. We know we can always go graphically, but if the y's aren't approaching an integer value, then it might be hard for us to see what it would be if I try to always do it graphically. If I did the trace button on my graphing calculator, I could get approximations if they were integers, but I'd still not have exact values. I want to have some sort of analytical way of doing this so that I could get my values of my limits without having approximations, and also for some of them, maybe get them without graphing. And that's what we're building towards. So let's do these examples. So here it's the limit as x approaches 3 of x to the 4th. So this particular one matches that third of the basic limits that we're looking at. And so this will come out to be 3 to the 4th by our definition up there, and 3 to the 4th is 81. Now when I want to report it, I have to say the limit as x approaches 3 of x to the 4th equals 81. I can't just say the limit equals 81 because you've got to have an argument that the limit is acting on to know what function you're looking at. And I can't forget to put as x approaches the number on the bottom, or I wouldn't know where on the graph I was looking. So you need all of that notation to answer appropriately with full notation. Let's do part B. Part B is the limit as x approaches 5 of the number 2. So notice there's no letter here that matches the letter of the limiting process. So this one matches with this first, the limit as x approaches a value of a number. And remember, when the limit as x approaches a value of a number, y equal that number is a horizontal line, and the outputs are always approaching that horizontal line output value. So here, my value is going to be 2. Next up, the limit as x approaches -1 of pi. Well, pi is a number, and it doesn't have an x after it, so it doesn't have the variable of the limiting process. So the limit as x approaches -1 of pi, again, is this first limit rule. And so this is just going to be pi. Next up, the limit as x approaches -2 of x. So now I am acting on the variable of the limiting process. And the limit as x approaches a value of x is just the value that it's approaching, because it's on this line, y equal x. So the outputs are approaching what the inputs are when you have your argument here just to be x. So the limit as x approaches -2 of x is -2. How about the limit as x approaches pi of x? Well, again, it's this second one, and so that will be pi. And then for our last part, the limit as x approaches -3 of x squared, that is this third one, and so that's going to be -3 in parentheses squared. So the limit as x approaches -3 of x squared is equal to 9. We're now going to build some basic properties of limits with function notation, and then after this and talking through that, I will give you some different examples with actual functions in place and have you refer back to these rules that you'll have in your notes. So let b and c be real numbers, and let n be a positive integer. So again, the n has to be 1, 2, 3, 4, 5, 6, etc. And then let f and g be functions such that we have that the limit as x approaches c of f of x is L, and the limit as x approaches c of g of x is K. So they're both approaching the same x value for these two different functions. So then you have your value that the x is approaching is the same, but you have two different functions that you're looking at, so their limiting values might be different. So first of all, this is called the scalar multiple rule of property of limits. So this says, if you're taking a limit as x approaches a value of a number times a function, and you already know the limit as x approaches that particular value of the function itself is this L, well, when you have a number factor times your function, or actually a factor times your function that's not the variable of the limiting process, then you can pull that factor out in front of the limit, and then that factor comes out in front, and then you can replace this limit as x approaches c of f of x with the limit that it is equal to, and ultimately get that that is b times L. Next up, the limit as x approaches c of either an addition or a subtraction of two functions who have a limit and you know what their limits are. Now this property actually could have had another step that I could have written in it, and that is that if you're taking the limit as x approaches a value of an addition or a subtraction of two functions that you know have a limit, then it's the limit of the first function plus or minus the limit as x approaches that value of the second function. So the limit of a sum of two functions is the sum of the limits of the two functions. So then I just have our limit as x approaches c of f of x is L, then plus, and I needed a plus or minus here, then plus, when I'm doing an addition between the two functions, the limit as x approaches c of g of x is k. And if you're doing the subtraction of the two functions, the limit as x approaches c of f of x minus g of x would equal L minus k. So top path for the top path and lower path for the lower path. Next up, the limit as x approaches c of f of x times g of x. So this is a limit of a product of two functions that you know have a limit individually and what their limits are. So the limit as x approaches c of f of x times g of x is a limit as x approaches c of the first function f of x, and multiply that to the limit as x approaches c of g of x. Well, the limit as x approaches c of f of x is L, and we're going to multiply that by the limit as x approaches c of g of x is k. So the limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits as long as the limit as x approaches c of g of x is not 0. So as long as I won't get a 0 in the denominator of the fraction. So here we're just going to say that k can't be 0. And then lastly, the limit as x approaches c of f of x to the n. So if I have a positive integer power on my base function, and I want the limit as x approaches it, and individually I had that its limit exists and what its limit is, then the limit of a function to a positive integer power is the positive integer power of the limit, so then that's going to give me L to the n. So what we're going to do next is erase this and then put up some examples, apply the properties that we learned to each of these examples. So the first one, it's asking me to find the limit as x approaches 5 of 2x minus 4. Now remember, so far we only have that the limit as x approaches a value of a number is that number. The limit as x approaches a value of x is the value x is approaching. And the limit as x approaches a value of x to a positive integer power is the value that x is approaching to that positive integer power. Those are the only ones we've built so far in our foundation. We'll get more, but right now we can only deal with the ones that we have. But then we just have those properties that said that the limit of a scalar times a function is the scalar times the limit of the function. When I'm taking the limit of the addition or subtraction of two different functions that alone have limits, and I know what they are, I just do that addition or subtraction. And then we had the product, the limit of a product is the product of the limits. Again, if those individual limits exist. The limit of a quotient is the quotient of the limits if the individual limits exist and the denominator is not going to 0. And then the limit of a function to a positive integer power is that positive power of the limit of that function. So how are we going to deal with these then? Because basically they're not actually matching our original few limits that we know. But it is addition or subtractions or multiplications or things like that. So we're going to apply our properties. Now the first one, I'm going to scoot this up and make it a little bit smaller. The first one is the limit of two different terms. And I can break this up as the limit as x approaches 5 of the first term 2x minus the limit as x approaches 5 of the second term 4. So that's just the limit of a subtraction of two functions is the subtraction of the two limits. Now in the first term, I have 2 multiplied to my x. So that's a scalar factor that I can pull out in front of the limit. So this is 2 times the limit as x approaches 5 of x minus, And then here, this is one that I know because it's the limit as x approaches a value of a number. So I'm just going to write that in so that I'm not on two different stages of the simplification when I'm there. Now that I've gotten these down to using my properties to be able to apply my original few limits that I know, I'm going to evaluate those limits, and then plug them in. So I have 2 times the limit as x approaches 5 of x. So remember, that's just going to be whatever you're approaching, so that's 5. Minus the limit as x approaches 5 of 4. That value is not the variable of the limiting process. It's just a constant value. So the limit as x approaches 5 of 4 is the number 4. Now we're going to use our order of operations. And so we've got our 2 times 5 is 10, subtract 4 gives me 6. So this gives me a limit of 6. And I want to write the limit as x approaches 5 of this quantity, 2x minus 4, is equal to 6. Let's look at the next one. Part B. Well, part B, this is just the limit as x approaches 7 of my scalar factor in front of my function. So with this number being attached by times, I can bring that factor out in front of the limiting process. So that's 3 times the limit as x approaches 7 of x. And then the limit as x approaches 7 of x, that's 7. So this gives me 3 times 7, and so this limit is 21. Next up, I have part C, and this is the limit as x approaches negative 2 of negative x squared minus 4x plus 1. And that negative x squared, I can think of that as a negative 1 in front of the x squared. So first off, I'm going to say the limit as x approaches negative 2 of several different terms is the limit of each of those terms individually, because that is the limit of a sum or difference is the sum or difference of the limits. So this is the limit as x approaches negative 2 of my negative x squared minus the limit as x approaches negative 2 of my 4x plus the limit as x approaches negative 2 of 1. For each of these with a scalar multiple, I can bring them out front. So this is negative the limit as x approaches negative 2 of x squared. Then minus 4 times the limit as x approaches negative 2 of x. And then plus the limit as x approaches negative 2 of 1. And now we're going to evaluate the limits and multiply by the scalars at the same time just to have enough space. So I've got my negative. The limit as x approaches negative 2 of x squared, well, that's negative 2 squared. And negative 2 quantity in parentheses squared is a 4. So I get a 4 for this limiting process, but I have the minus that came down. So this is a negative 4. And then minus 4 times my limit as x approaches negative 2 of x. Well, that's just going to approach as its outputs what the inputs approach. So that's going to be negative 2. And then plus the limit as x approaches negative 2 of a constant 1 is just 1. So that gives me negative 4 plus 8 plus 1, so that's going to give me 5. Okay, then next step is if I already know that the limit as x approaches 5 of f of x is 9, and I also know that the limit as x approaches 5, it's approaching 5 in both cases, of this other function g of x is negative 2, I want to find the limit as x approaches 5, the same value is approaching, of 3 times f of x minus 4 times g of x. So here, because they didn't give me the actual functions for f of x and g of x, they actually did give me what their limiting values were as x approached those values. So we want to use our properties. So first off, the limit of a sum or difference is the sum or difference of the limits. So this is the limit as x approaches 5 of 3 times f of x minus the limit as x approaches 5 of 4 times g of x. Now we're going to pull out the scalar factors that are in our argument that the limit is acting on. So the limit as x approaches 5 of 3 times f of x is 3 times the limit as x approaches 5 of f of x. And I have a minus the limit as x approaches 5 of 4 times g of x is minus 4 times the limit as x approaches 5 of g of x. And now I go look and see if I know what these limits are. What's 3 times? Well, the limit as x approaches 5 of f of x, in the setup of the problem, they told me the limit as x approaches 5 of f of x is 9. So that entire notation comes out and a 9 goes in. Minus 4 times the limit as x approaches 5 of g of x is negative 2. So that gives me 27 plus 8, and I get a limit of 35. So this limit, that is equal to 35. So this gives you an example of what if they actually have functions that the limit's acting on, or what if I already know what the limits of the functions by name as x approaches a value, what their limits are, and then they want me to apply the properties to find a limit of a function that's created from scalar multiples, addition, subtraction, maybe multiplication, division, etc. Now it's really important that you show the work for these steps when you're first doing the limits and you don't have other properties to depend on, because this actually helps you just reinforce what the properties are and how you can appropriately then apply them. Here's a few more that are handy to know. If p of x is a polynomial, remember a polynomial is an algebraic expression in which the exponents on the variables are whole numbers, and c is a real number, then the limit as x approaches c of a polynomial function, p of x, is equal to p of c. So once I have this theorem and I realize the limit is acting on a polynomial, I can find the limit of that expression of the limit as x approaches c of that polynomial by just plugging the value through the x's in the polynomial. But I needed this theorem before I could just jump to that without using the individual properties. Now, next up, if r of x is a rational function that's formed by a polynomial divided by a polynomial. That's what a rational function means. It's a polynomial divided by a polynomial. And c is a real number such that if I ran it through the denominator polynomial, I don't get a 0 out. Then the limit as x approaches c of that rational function is just putting in the value that the x is approaching for the x's in the numerator as well as the denominator. Also, we have that for trigonometric functions, if you have c, the value that x is approaching, is in the domain of the given function that you're doing the limits of, then the limit as x approaches c of sine of x is just sine of c. The limit as x approaches c of cosine of x is just cosine of c. The limit as x approaches c of tangent of x is just tangent of c as long as tangent of c is defined. The limit as x approaches c of cotangent of x is cotangent of c as long as cotangent of c is defined. The limit as x approaches c of cosecant of x is cosecant of c as long as cosecant of c is defined. And the limit as x approaches c of secant of x is secant of c, again, as long as secant of c is defined. Now with the polynomial ones, we actually did a few of them already as examples, but we applied all of our properties of limits to get to it. What we're going to do next is to just do a couple examples of these other ones. Okay, so now let's look at these examples. The first one, part A, is the limit as x approaches 4 of x squared minus x minus 1 over x plus 3. Now the first thing I look at is to make sure that the value that the x is approaching does not make the denominator 0. Well, 4 plus 3 is 7. I don't have any trouble with having a 0 in the denominator. And this is a polynomial. Exponents are whole numbers divided by a polynomial. So I can just use that rational function theorem with limits that says the limit as x approaches a value of a rational function is just going to be the rational function evaluated at the number as long as the number doesn't give you a 0 in the denominator, which this doesn't. So I'll have a 7 in the denominator, and in the numerator we have our 4 squared minus 4 minus 1. So that gives me 16 minus 4 is 12, minus 1 is 11, so I get 11 sevenths. So this limit is 11 sevenths. And again, there would be a lot more writing out before I got to the theorem about the rational functions, because I would have to apply all of my properties of limits to get there. But now that I have the rational function limit theorem, and I'm able to go here. Next up, the limit as x approaches pi over 4 of sine of x. Well, sine of x's domain is all reals. So I am just going to get the sine of pi over 4. And the sine of pi over 4 is the square root of 2 over 2. So since I have that the sine of x is continuous at pi over 4, the values that the y's will approach as I get infinitely close to pi over 4 is the same thing as what the limit is there, because it's a continuous function there. So my limit as x approaches pi over 4 of sine of x is also the square root of 2 over 2. Next up, the limit as x approaches negative pi over 2 of cosine of x. Well, that is the cosine of negative pi over 2. And remember, if you're thinking about it through the unit circle way, the negative angles, trig angles in standard position, you go down and around. So if you're going down to negative pi over 2 and then looking at your cosine of negative pi over 2, well, that's actually just going to give you 0. How about the limit as x approaches negative pi over 4 of tangent of x? Well, that's just the tangent of negative pi over 4 by that theorem of limits of trig functions. Negative pi over 4 is in the domain of the tangent function. So I think negative pi over 4 is in the 4th quadrant, and the tangent of a pi over 4 angle in general is a 1, but in the 4th quadrant, it's going to give me a tangent value of negative 1. How about the limit as x approaches pi over 6 of sine x? Well, that's the sine of pi over 6, and the sine of pi over 6 is 1/2. And then the limit as x approaches 5 pi over 6 of cosine x, that's in the 2nd quadrant, and that's going to give me a negative square root of 3 over 2. Now I know I went through these quickly in terms of the values of the trig functions evaluated at those nice angles in radian measure, which I need them in because the trig functions have to be acting on a real number for its graphs and for the work with this. But if you don't remember them or just need a little bit of refresher, I've linked also the the videos that I've made on trig functions of nice angles and reference angles in the description of this video as well. Well, hopefully that gives you a start of some of the very beginning parts of our limits and working with them analytically. Look for more videos that I'll post up of other properties and other theorems of limits that will help us greatly as we move through this material.